Boyd King at OSUIT in the air conditioning department. We're going to do a section on single-phase motor starters. Up to this point, we've been through motors, our section on motors, and learned about shaded pole motors, split-phase motors, three-phase motors, capacitor start induction run, PSC motors, and so our next step is adding starting components. We can call them hard start kits, we can call them components to take out the start capacitor, but there's three categories that we can find motor starters. One is going to be a PTCR, that stands for positive temperature coefficient thermistor. Two is going to be a current relay, usually on small compressors, ice makers, reach-in refrigerators, domestic refrigerators, water fountains, things like that, where you will see current relays. Larger compressors, residential, especially light commercial, rooftop package units, you're going to see single phase. Now these are non-three-phase motors. Split phase motors is what we're building off of still, but we're going to see a lot of potential relays. Okay, example, here is the guts basically out of a Trane residential unit, and you can see right here there is a potential relay and a start capacitor. That's what makes this residential unit start up. Okay, so very, very common in our industry. Understanding capacitor start and capacitor run compressors is a must. One of the most misunderstood and I think misdiagnosed parts of our industry is technicians out there working that do not understand, especially potential relays. So up to this point, what you should have done is you should have already been over and looked at the PowerPoint for single-phase motor starters. You should be done with compressors. If you're watching this video before you have went through the PowerPoint on motor starters, you can go ahead and watch it, go back to the PowerPoint, and then come back and watch this again. The main purpose in this video is for me to step-by-step explain the order of operation of how these two relays work. I'm not going to spend a lot of time on PTCRs. We will again in residential and in unitary refrigeration, but I do want you to be introduced to current relays and potential relays. Okay, so looking at being able to identify the two, the PowerPoint done a pretty good job showing you the two. A current relay we're going to be able to identify because usually the coil, you can see it. It will be opened up and it slides directly onto the compressor, a couple of terminals there. You can hear the contact shaking in there. This is a positional, meaning it has to be installed in the correct position. Has a set of positional contacts, non-spring activated. So they are meant to be normally open contacts, not normally closed. And so if you were to install these upside down, the contact would be closed and it would not work correctly. So they slide on most of the time to make sure that you cannot positionally miswire them. These should be very, very low resistance, from 1 ohm down, very small resistance. They're meant to be an impedance circuit that we will learn later on. Okay, identifying and being able to see a potential relay. Potential relays are usually black boxes, sometimes white or gray. They'll be located inside the control panel, and they will have usually numbers on them that say 5, 2, and 1. Very crucial to memorize. Some technicians call these 5, 2, 1 relays. The current relays, they'll have 3 terminals, L, M, and S. Line, L, S start, and M is motor. Okay, so we'll talk about how to wire using those terminals on those. Okay, so let's start talking about a current relay first. Current relay we can identify in a diagram that we're dealing with a current relay and not a potential relay, because the current relay coil is wired directly in series with the start winding. We don't see that very often in our industry where we use loads in series. Current relays are, wired in series with the run winding. And the normally open contacts are in series with the start capacitor. Okay, so how do these start and run? This is the main point in me doing this video, for you to pay attention to how a current relay operates. At startup, we have a path into common through the run winding, through the current relay to the other side of the line. We do not have a path through the start winding or the start capacitor. So the motor cannot start at startup. Why don't we have a path? Because that contact is a normally open contact. So what will happen to a motor trying to start and not being able to start? For a split second, this motor is going to pull a massive amount of current, locked rotor current, through the run winding and through the current relay coil. That high current creates an electromagnetic force which picks up the armature, closes the contact, brings in the start capacitor and the start winding. The motor then starts and runs. At that point, because the motor starts and gets up to speed, the current is going to fall through the current relay, falls below the dropout voltage, which opens the contact back, takes back out the start capacitor and the start winding, and the motor runs as an inductive load. So once again, real quickly, have a path at startup. We have a path through the run winding, through the current relay. We do not have a path through the start winding or the start capacitor. The motor can't start. It pulls locked rotor current. It pulls high current through the coil, which creates an electromagnetic force, picks up the armature, closes this contact, brings in the start capacitor and the start winding, gives it a sense of direction. Motor starts. At that point, when the motor starts, the current falls lower than the dropout voltage, drops the contact out, takes out the start capacitor and the start winding, and the motor runs as a inductive load. Potential relays, here's how they start and work. Well, let's talk about how they're wired first. Remember, these are called 521s. They're the little black box. And there is a saying that goes along with how to wire these. It is 2, sir, 5, let's see. 2, sir, 5, C. 2 goes to start. 1, or I, 1, goes back to run. And 5 goes to common. 2, sir, 5, C. 2, sir, 5, C. It's a saying on how to wire these. That is how I made it through my journeyman's test. Don't ever forget that. 2, sir, 5, C. So 5 goes to common, 2 goes to start, 1 goes back to the run capacitor. So you can see I have drawn here a split phase motor at a run capacitor. It's a PSC motor, makes it a PSC, and now we're going to add a start capacitor. We have to take the start capacitor out of the circuit. So highest starting torque of all the single phase motors, high starting torque, high running torque, and it's a great combination for compressors and single phase compressors. So how does it start and run? You can see that we have a path coming in through our overload, and if you were to break this down, you would have an electrical path through every load. Here's the load, run winding, load, start winding, run capacitor, start capacitor, and the potential relay coil through a normally closed contact. Okay, so the way I explain how this works, at startup, all loads energize. All loads energize. Because you have a start winding and a start capacitor, you automatically have a sense of direction and starting torque. So the motor starts, it begins spinning, it gets up to 75 to 80% of its total speed. Because a motor is spinning, we've learned that it induces a voltage between common and start. That's called high induced voltage between common and start. It reaches, because it's spinning fast enough, it produces enough induced voltage to reach the pickup voltage of the potential relay, which opens the contact, which takes out the start capacitor, and the motor runs now as a PSC motor. When you take the start capacitor out of the circuit, that extra current flow through the start winding decreases. So it becomes less inductive, which keeps the, it allowed it to drop out, but it keeps the potential relay energized, holding open the contact while it's running. So the high induced voltage drops, but it does not drop below the dropout voltage. So once again, how does this start and run? Potential relays, capacitor start, capacitor run with potential relays. All loads energize at startup. All loads energize. Because all loads energize, the start winding, the start capacitors in the circuit, gives it increased starting torque, gives it a sense of direction. The motor starts. It gets up to 75 to 80% of its total speed. Because it's spinning, it produces a high induced voltage between common and start, which is wired parallel. The potential relay is wired parallel to common and start. So it sees that high induced voltage. It reaches the pickup voltage of the potential relay, opens the contact, takes out the start capacitor. The motor continues to run as a PSC motor. Because the current flow drops through the current relay, the high induced voltage drops, but not below the dropout voltage. So the relay remains energized, holding open the contact so that the start capacitor does not come back in the circuit. Listen to this video 2 or 3 times, focusing on, and you may even want to write down, pause it and write down every single step of how each one of these starting components start the motor and then allow the motor to continue to run. Please email me if you have any questions about this, and make sure that you're looking at all of the content out there on motor starters along with this video. I will be posting some assignments later on. Thanks a lot. Have a good day.